Hi everybody. The point of this video will be to give a few more details and to give a very simple example illustrating Richardson extrapolation. So let's start with the following kind of problem. Let's say that we have a problem domain here stretching from x equals 0 to x equals L. And let's suppose that our original number of nodes is just 3. So we have, and in every case, that is for every iteration, we are going to use uniform spacing. So in other words, the spacing between any two consecutive nodes is the same regardless of the of where you are in the mesh. So at this first iteration where we have 3 nodes, then we would see that here is delta and here is delta, and so delta is equal to L divided by n minus 1, where n is the number of nodes, and in the first iteration n is equal to 3, so it's L over 3 minus 1, or L over 2. And that's very clear that the that this first segment would have a length of L over 2, and then this would have a length of L over 2. Now, the equation that we are looking at in this problem, in this project, is the following. We have d squared v, or u, perhaps, d squared u dx squared plus k squared u is equal to 0. And then this is a second order differential equation, so we need 2 boundary conditions. And the 2 boundary conditions we've been using are u of 0 is equal to a, and u of L is equal to b. Now, when we use the finite difference approximation for the second derivative, we get u of I plus 1 plus u of I minus 1 minus 2ui over delta squared plus k squared ui equals 0. Now that's what we get by enforcing this differential equation right here at node I, and then using the finite difference approximation for the second derivative. So if we take the resulting discretized equation and we multiply through by delta squared, actually you don't need to do that if you don't want to, but if you do choose to multiply through by delta squared, then you would get ui plus 1 plus ui minus 1 plus ui times k squared delta squared minus 2 is equal to 0. So let's go ahead, for the sake of illustration, let's go ahead and assume that in this particular problem, L is equal to, well, maybe it's better to leave this sort of general, at least for the moment. So let's think about that. Okay, so this is the equation at node I. where I can be any interior node. Now, we don't enforce that equation at the boundary nodes. There, we need to enforce the boundary conditions. But at interior nodes, we would enforce that equation. So, for instance, in this first case where we have just 3 nodes, then we would, n equals 3. Okay, at our first node, we have u1 is equal to a. Because u1 here, we're talking about the node at the leftmost boundary. For u2, we will have u3 plus u1 plus u2 times k squared delta squared minus 2 is equal to 0. So this is the equation we get at node 1. This is the equation we get at node 2. And then at node 3, that's another boundary node, so we would have u3 is equal to b. So when we write notice that we have here 3 equations and 3 unknowns, and so when we write this in matrix form, what we will get is the following: 1, 0, 0, 1, 1, and k squared delta squared minus 2, and 0, 0, 1. u1, u2, u3 is equal to a, 0, b. So that would be the matrix equation that we would have for the first iteration. And this is similar to work you've done on previous projects. And you would, of course, create that matrix and create this forcing vector for the right-hand side, and then you would multiply that forcing vector. You would pre-multiply it by the inverse of the matrix, and you could get your solution. And then if you wanted to know the error in your solution, you would use the error formula that we've discussed before in class. Now, what we would like to do, the idea of the Richardson extrapolate is that we want to try to get a more accurate solution. And to get a more accurate solution, what we're going to do is to combine this solution with another one obtained by using a finer discretization. And so let's see how that would go. We look again at our current mesh, and remember what we currently have is this. This is from step 1. But now we're going to go to step 2. And the rule is going to always be the same here. Whenever we go from one step to another, we will introduce new nodes at the midpoint of every segment in the existing mesh. So as we go from step 1 to step 2, we have here in the existing mesh, we have 2 segments. One between node 1 and 2, and another segment between node 2 and 3. And so when we go to step 2, we're going to put one additional node here in the middle of segment 1, and another node in the middle of segment 2. Now remember that in the step 1, our nodes were numbered like this: 1, 2, and 3. And if we still number from left to right, which is certainly what I would recommend to you, then in step 2 we will have 1, 2, 3, 4, and 5. Now, we don't need to try to get a more accurate solution. When we're looking here at step 1, we don't need to try to get a more accurate solution at node 1 because we have the exact value there. That's the boundary condition. And likewise, we don't need to try to get a more accurate solution at node 3. It's also a boundary condition. But at interior nodes, we would expect that we probably have error, and that's where we would like to get more accurate solutions. So in step 1, we just have one interior node, and that's node 2. And notice that it matches up exactly with node 3 in step 2. So the idea here is that we're going to go ahead and look at step 2. Now for step 2, notice that now delta for step 2, delta is now equal to L over 5 minus 1, which is L over 4. So maybe I'll put this as delta 2, and up here I'll say delta 1. And likewise here in this equation, I'll say delta 1 to make sure that there's no ambiguity, because we definitely are changing the delta as we go from step to step. So if I put that subscript of 1 everywhere there, we will get that. And then here in step 2, we would have then, when we look at our equations, U1 is equal to A, and then we'll have U3 well, let's maybe do it this way. We're still going to use this formula right here, but when we go to step 2, instead of using delta 1 squared, we'll use delta 2 squared. So what this will become then at node 2, we will have U3 plus U1 plus U2 times k squared delta 2 squared minus 2 is equal to 0. This is the equation at node 1. Here's the equation at node 2. We're also going to have an equation at node 3, node 4, and node 5. And those will be easy. This will be, at node 3, we have U4 plus U2 plus U3 times k squared delta 2 squared minus 2 is equal to 0. And then at node 4, U5 plus U3 plus U4 times k squared delta 2 squared minus 2 is equal to 0. And then finally at node 5, that's the boundary node, so U5 is equal to B. And so now we will, instead of having we have 5 equations and 5 unknowns now. So instead of having a 3 by 3 system like we do here, this is step 1. Now we'll get a 5 by 5 system that will look something like this. We'll have 1, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1. You see, that's 4 rows, and then row 5. And then we'll have 0, 0, 0. And now for the other entries, we have k squared delta 2 squared minus 2, k squared delta 2 squared minus 2, k squared delta 2 squared minus 2, u1, u2, u3, u4, u5, a0, 0, 0, b. And so this is what we would have at step 2. And now the crucial point for the Richardson extrapolation, again, we've already mentioned it, but let's just go to it again. We expect, looking here at our meshes for step 1 and step 2, since we have more nodes in step 2, we expect it in general to be more accurate. So in general, we would expect the solution at node 3 in the step 2, here, this I'm talking about right here, we would expect the solution there to be more accurate than the solution up here from the first step, because in the second step there are more nodes. But it turns out that by using the formula for the Richardson extrapolate, that we can get an even more accurate solution. So let's review that for just a moment. So the Richardson extrapolate says that we, here's the formula right here for the Richardson extrapolate. Well, here, let me actually erase that. So this is the part we want right here. So the way that would translate for what we're doing, we have 4 minus 1 over 3, okay? So we have after we've gone for 2 steps, we would have Richardson extrapolate at x equals L over 2. This is at the midpoint of the mesh, which corresponds to node 3 in step 2, but to node 2 in step 1. That's a tricky part, is you need to, as you go from one step to the next, you need to keep in mind that the node numbers are changing. And so our Richardson extrapolate would be 4 times U3 from step 2 minus U2 from step 1 over 3. This, again, is corresponding to this equation right here. You have 4 times your numerical solution from one spacing minus 1 times your numerical solution with double that spacing divided by 3. Now, another way, perhaps a less confusing way to write this is just to say for u of L over 2 step 2 minus u at L over 2 from step 1 over 3. But the benefit of the previous way of writing the Richardson extrapolate is that it emphasizes that there are different node numbers in the two solutions. So anyway, this is you could regard either one of these as your formula for the Richardson extrapolate at that point. And the thing that's interesting is that the Richardson extrapolate will be, in general, it will be more accurate than the solution from either step 1 or step 2. So the remarkable thing here is that we take two solutions. Now, of course, the solution from step 2 should be more accurate than the solution from step 1, but by combining the solutions from steps 1 and 2, we actually get the Richardson extrapolate, which is more accurate than either. And so that is the way that the Richardson extrapolate is formed. Now, in going from step 1 to step 2, there's only that one node where we could calculate the Richardson extrapolate. As we go from step 2 to step 4, though, we could calculate a Richardson extrapolate at several nodes. So let's look at that. So step 2 had 5 nodes. One, two, three, 4, 5. And then step 3, again, when we go from one step to another, we simply put a node in the middle of every existing segment. So we're going to put another node here, another node here, another node here, and another node here. So, and then we have our nodes at these points. And then we number them 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so now we could calculate a Richardson extrapolate here at x equals L over 4. We could calculate a Richardson extrapolate at x equals L over 2. And finally, we could calculate a Richardson extrapolate at x equals 3L over 4. So at this next stage, we would have 3 values in the Richardson extrapolated solution, and so on. So at each step, we get more and more nodes at which we can calculate a Richardson extrapolate, and we calculate at each step the global error in the Richardson extrapolate in the exactly the same way we have before. The global error is equal to the square root of the sum I equals interior nodes of U numerical of I minus U exact at I squared divided by number of interior nodes. So, for the first step, then you only had the Richardson extrapolate at that midpoint. So the global error there is equal to the error at just that one point. But then when you go to the next step, well, here we have 3 points in the Richardson extrapolate. So we would need to sum over those 3 points where we have a Richardson extrapolate solution. And at each one of those nodes, we would calculate the Richardson extrapolate, subtract from it the exact solution, and then square that. We do that at each node and then add up what we get at each time. After we add that all up, we divide it by the number of interior nodes, in other words, the number of nodes at which we're calculating this Richardson extrapolate. And then finally, after we do that, we take the square root, and that'll be our global error. And with each iteration, we can calculate a new Richardson extrapolate and then a new global error. And in the end, what we want to do is to plot the log of the global error versus the log of the spacing. And we've already seen that for the original solution, that gives us a graph of slope 2. But with the Richardson extrapolate, we're going to find that we'll get a graph with a higher slope because as a result of the fact that the way that we're combining these solutions at each step to get the Richardson extrapolate gives us a solution, the Richardson extrapolate solution, which has an error that's getting smaller very quickly as delta gets smaller. So that is the point of this project. So again, what you'll do, just to give you an overall view, you need to solve this problem over and over, and each time you will introduce nodes at the midpoints between existing nodes. So you're going to get more and more nodes with each step. And also at each step, you will combine 2 solutions to get a Richardson extrapolate solution. And you'll need, at each step, with your Richardson extrapolate solution, you'll need to calculate the global error so that you can keep track of the global error in the Richardson extrapolate solution as a function of the spacing. Because in the end, you're going to want to plot the log of that global error versus the log of the spacing. So hopefully this will clear up some of the any hesitations about the Richardson extrapolate solution.